Hi everyone, I'm Rattana, and today I'll be talking about my joint work with Nina, Pradeep, and Hongyang on Nash Equilibria and Pitfalls of Adversarial Training in Adversarial Robustness Games. There are many real-world applications of machine learning systems. However, there usually is a mismatch between the environment which the ML algorithms are trained and the condition which they are deployed. Making sure that the ML systems are robust to a potential change in the environment is crucial for safe and reliable deployment. In this work, we focus on the adversarial robustness setting, where we assume that there exists an adversary that can perturb a test point with the goal to change the model prediction. It is known that there exists an adversary that can do this with only a small perturbation. We view this problem of learning a robust model through lens of two-player zero-sum games between an attacker that chooses how to perturb data points and a defender that chooses a model that still performs well under the perturbed data point. So we set the utility of the attacker to be the expected loss of the model given the data is perturbed by the attacker, and the utility of the defender to be the negative utility of the attacker. In particular, we made the following assumption on the data distribution and the model. So first, we are learning a binary classification. We assume that features are independent given the label, and the mean of each feature are symmetrical. We also learn a linear model, and we assume that the perturbation set is an L infinity ball with a radius epsilon. And we call this epsilon the perturbation budget. And we call this symmetric linearized adversarial robustness game, or SLAR game. Here's an illustration of the data distribution. Each color represents each label class. So we can see that the mean of each class are symmetrical. But we know that we do not have any additional assumption on the distribution. So as long as the mean are symmetrical, this distribution can have any shape. And we want to learn a linear classifier that separates these two classes. With the perturbation budget of epsilon, we have two types of features. First, robust feature are features that the mean is larger than the perturbation budget. The picture is on the left, so we can imagine that robust features are features that each class are far away from each other. We also have non-robust feature where the mean of each class is smaller than the perturbation budget. So you can see this feature as a feature that these two classes are close to each other. First, we remark that adversarial training, which is a standard technique for training a robust model, has a strong connection with an alternating best response strategy in this game. In adversarial training, we do the following. First, given a correct model, we find adversarial examples that our current model does not perform well. And then we update our model to correctly classify this adversarial example. So in the context of our game, at each time t, an attacker find the perturbation that maximizes the expected loss given the current model. So maximizing its utility. And then the defender then find a model that best responds to the perturbation from the attacker. So each player is playing a response that maximizes the utility given the action from the latest action from the attacker or the defender, respectively. However, we know that this is an approximation because in practice, we use stochastic gradient descent and projected gradient descent. For the first result, we show that if the number of non-robust features are large enough, then adversarial training may not converge. So we call that non-robust feature are feature that the mean of that feature is smaller than the perturbation budget. Next, we also consider a Nash equilibrium of the game. So we recall that a pair of a perturbation function and the model is a pure strategy Nash equilibrium when each player cannot improve their utility by changing their action unilaterally. When our model is at the Nash equilibrium, then we know that, say, an attacker cannot improve their utility by changing the action. So it means that at the Nash equilibrium, there is no attack that increase the expected loss. So this might be an interesting scenario because if we know that we are at the Nash equilibrium, then an attacker cannot improve their utility. So we know that the robustness we have is the best robustness that we can attain. And this may help mitigate the scenario when we have a new defense and then like this defense is broken a few months after that because there's a new attack that is specific to that defense. If you add a Nash equilibrium, this would not happen. In the paper, we show that for the SLAR game, there exists a unique Nash equilibrium. And this Nash equilibrium is robust. We can also directly solve for this Nash equilibrium by using a closed form worst case perturbation given by a model. And we call this optimal adversarial training. To recap, we show that adversarial training may not converge. Nash equilibrium of the SLAR game exists and is robust. And it is possible to solve directly for the Nash equilibrium for this game. We provide additional experiment results on MNIST dataset in the full paper. Thank you.